In the previous lecture, we have discussed about minimizing switch capacitance. The product of switching activity and CL is called as switch capacitance. Whenever you minimize this, switch capacitance can be minimized. In other units, we have seen how voltage scaling is done. In this unit, we will discuss in minimizing the power dissipation, dynamic power dissipation. You need to minimize this factor. For this, we have different techniques. The first technique was like system level degradation, in which you have hardware software co-design. Using hardware software co-design, you've been minimizing the switching activity and capacitance. In this technique, using bus encoding, you can also reduce alpha CL. In the bus, you'll be having the information to be transferred. In the bus, you have the bits that are intended to transfer from transmitter to receiver. By proper encoding the data on the bus, we can control the switching activity of the data that is being transmitted. Here, encoding is basically used in transmitting the data from one point to another point. In a communication, bits are transmitted one after the other. While transmitting, we have to remove correlation between the bits, which can be performed by encoding. That is, through encoding, we perform some encryption, which is helpful for having the security of the data. The data cannot be identified by others. This can be done in different ways. Using different techniques, we have encoding process. Based on the redundancy, broadly you have two types. We can say like based on redundancy, encoding techniques can be given as non-redundant and redundant. In non-redundant, based on your mapping process, you have one-to-one encoding technique. Here, in redundant, you may have either one-to-one or one-to-many. We'll see briefly about these things in this lecture. Here, this is a sender chip, this is a receiver chip. Sender will have n number of bits to transmit, whereas the receiver may receive the same n number of bits, or it may be a encoded form, which may be given as m bits. Decoder, after receiving these bits, again converts into the same number of bits given by the sender. N number of bits are received here. This is a simple block diagram which represents encoder and decoders. Here, these two are used for reducing the switching activity, alpha value. whenever you say classification of encoding techniques, non-redundant and redundant. In non-redundant, you have n bit code is translated to n bits. In the sense, when it is being encoded, the transmitted bits are equal in a non-redundant technique. N equal to m. Whereas in a redundant technique, m is either greater than m or equal to m. You may not have compulsorily equality here. When you say when you're speaking about a redundant technique, here you don't have m equal to n. That is, after decoding, the number of bits m are greater than n here. This is the second type of encoding technique. Let us consider some of the encoding techniques. First is gray coding. In the gray coding, we will be having like a simple formation. We use a mirror image. For example, if you are encoding 1-bit code, binary code to gray code, you will be having 1 and 0. One-bit code is, binary code is either it is 0 or 1. Here, the same code is considered. There is no change here. Both binary and gray codes are same for 1-bit code. Whenever you are considering 2 bits, combinations are given as 0001, 10, and 11. Now, for the first bit, you'll be having a mirror image. This mirror image is given as 10, and the second bit is forwarded as it is 0011. Now, whenever you are considering 3-bit code, now these first 2 bits are being mirror imaged. So can you get the mirror image of this? 10, next 11, 0, 1, 0, 0. And if you're considering 3 bits combination, you'll be having the inputs like ones. 2 bits are given by a mirror image. This is a 2-bit combination. This is mirror imaged here. Now, for the third bit, you just transfer the bit combination as it is here: 00, 00, 00, 00, and 4, 1, 1, 1, 1. Right? In this way, you'll be forming 1-bit, 2-bit, 3-bit gray code. Here you can see the 4-bit combination. Okay. Here you'll be taking the mirror image after this point. Okay. Here it is 100, and this bit 01. Here it is mirror imaged 011. 111 is mirror imaged here, and here it is mirror imaged. Likewise, all are mirror imaged. Finally, you get 00, and the 4th bit is transferred. This all 4th bits zeros are transmitted from this point to this location, all zeros, and similarly all ones are transmitted here, and it is placed as ones in the 4th bit location. In this way, you'll be forming a gray code. Now, whenever you're forming a gray code, whenever you're transmitting the data, we'll be using a gray code representation in encoding. Then what happens here is, how can you reduce the switching activity? It has been discussed now, because if you reduce the switching activity, you can reduce the power dissipation. Here, the main advantage in the gray code is that if you have a continuous address locations, when you are transmitting address on the database, you'll be having the continuous address locations. If you have a continuous address location, 1 bit change is enough here. Here you can see, here 2 bits are being changed. 0 is changed to 1, 1 is changed to 0 here. But whereas here Hamming code distance here is only 1 bit change in this code. And here 1-to-1 mapping is done here. Here mapping, here what you use is one-to-one mapping. Whenever you're using this, just one bit transition is being seen from between two consecutive memory locations. Then the switching activity is only one here. Whereas here, if you consider the switching activity is more, the same data is encoded in a code form and you're transmitting. On the bus, the switching activity is less. If the alpha is less, then the power dissipation is also less. By this, you can reduce the power dissipation. But the drawback here is this can be used for only the applications in which the data is maintained in consecutive locations. Address is maintained in a consecutive form. In continuous, you have 0, 1, 2, 3 continuously you have a consecutive form. Whereas random data will not have this situation. In the random data, number of transitions in binary code and gray code may be same. For that purpose, we may not use this. Then how can you have a hardware implementation of this gray code? At the encoder, you'll be having the XOR gates. First bit is being XORed with the next bit, and the XOR operation itself will give you the output of a gray code. Whenever you're decoding here, the XOR bit of received and the resultant, first two received bits and the resultant bit is being forwarded. Okay, this is the simple way in which you can transmit the data by converting the data into encoders. That is for converting the binary code into a gray code, you require XOR gates, and for converting a gray code into binary code, again for decoding purpose, you also have XOR gates. The way you're connecting them is different. By using the tabular column, you can analyze how the XOR gates are helpful for converting the data. And here, the simple comparison of instruction addresses for different programs, fast queues program is taken, QSAT program is taken, reducer, circuit, semi-group, NAND gate. Likewise, you have different programs. Instructions are maintained in the sequence. For that purpose, you have the transition is constant. It is more and it is maintained constant in binary code. It is less and it is also approximately maintained constant in gray code. Whereas in a data, it is in random. So both binary code and gray code has more switching activity here. In some cases, we may have more switching activity in the gray code itself, not in the binary code. For that purpose, only in the applications where the data is maintained in a sequence, then only we can use a gray code. When the data is random, we cannot use a gray code. When the data is random, you have other types of code converting, conversion or data encoding techniques are there. We'll discuss them in the next video. Thank you.